Hi everyone, you're watching the Space Channel. We often get requests to explain the nature of wave-particle duality. How is it that light can simultaneously exhibit the properties of both particles and waves? How is that even possible? And how does it manifest? Let's sort out these questions together. In everyday life, we often observe objects behaving like particles. For example, if you toss a ball upward, it will follow a well-defined trajectory and land on the ground at a single, precisely determined point. Similarly, in everyday life, we also observe the behavior of waves. For example, when music is playing or we're speaking, sound vibrations propagate through the air, and people hear them in different places. Or if you throw a stone into water, the surface waves created by the stone's impact will spread out in all directions and reach the shore at many points. At the level of microscopic particles, we observe that particles such as photons, electrons, protons, and others exhibit both particle-like and wave-like properties. To be more precise, not exactly at the same time, the wave properties manifest as these particles propagate, while the particle properties show up when they interact with other particles. But in the big picture, that doesn't change anything. Let's take a closer look at this phenomenon. If we release a single electron in a room, it will propagate like a wave in different directions at the same time. But when it reaches a wall, it will strike it at only one point. To understand how this happens, let's imagine an analogous situation with the more familiar case of sound waves. Suppose you're standing in a room with a bunch of other people. If sound waves behaved the way microscopic particles do, then when you shouted, they would spread out from you in all directions, but only one person in the room would hear your voice. Another example, the ripples on the surface of water from a thrown stone. They too would spread in all directions, like sound waves, but they would strike the shore at only a single point. It seems really strange, but for microscopic particles, that's perfectly normal. How can we actually illustrate the wave-particle duality of, say, an electron? The simplest way to visualize the electron is to picture it as a tiny speck of dust inside a drop of water. When the drop hits a surface, it spreads across it like a wave, and the speck could end up anywhere within that wave. The speck, our electron, is guided by the wave's motion. But if we set out to find exactly where it is, we'll find it at a single, definite point. The wave also determines the probability of finding the speck at each specific point. For example, if the drop splits into two unequal parts, the speck is more likely to end up in the larger part. In quantum mechanics, wave-particle duality works roughly the same way. Each particle is described by a wave defined by a wave function, a special mathematical function whose square gives the probability of finding the particle, our electron, at a particular location. This is precisely the essence of wave-particle duality. However, from nature's point of view, there's nothing unusual about this phenomenon. Nature doesn't know anything about particles or waves. For it, absolutely everything in the universe is both a particle and a wave at once. It's just that as an object's size increases, the wave-like properties become less and less noticeable, while the particle-like properties, on the contrary, become dominant. The particle-wave distinction is a human invention, which is why wave-particle duality seems strange to us. That's all for now. If you enjoyed the video, give it a like and subscribe to the channel. See you next time.